Hi, good to see you again. Welcome to Matrix Multiplication, an introduction to Algebra. What? Matrix Multiplication? How can you multiply boxes of numbers? And are we going to have Algebra in Boxland? Don't know what's going on here, but let's have a look. I've set some up. Looks like you can multiply matrices somehow. Don't know what this will do if you multiply by that or if you added that. There's another one, looks the same down there. This is going to be exciting stuff. I wonder what they're hanging about there doing. Well, here is, that looks like a definition of matrix multiplication. Better wait for that one. And here is matrix multiplication, again with no timesing sign. Well, it looks like you can do it, so let's go and have a look at a simplistic way of introducing matrix multiplication. Multiplying boxes of numbers, believe it or not. Come on down here and let's have a look. Matrix multiplication. Some screen clippings here from Hayes and Harris and their Year 12 Studies book. Let's have a look at the little problem they've got there. You go to shop and purchase those, and these are the costs of 3 soft drink cans, chocolate bars and ice creams. So we've done a bit of this before. You could let this column matrix represent the number of items of each you bought, and this row matrix here, the costs of them. So actually we've got here a 3 by 1 matrix, remember the order of matrices before, and a 1 by 3 matrix. Okay, so let's have a look then at what we might want to do. If we wanted the total cost of the purchase, we'd want to multiply the $1.30 by 3, that, and the 90 cents by 4. There'd be a certain match-up here that we'd want, and then the total cost would be $9.90. Well, what we do now to do those pairing ups or multiplications between matrices, and this is our fundamental definition of matrix multiplication, it actually consists of pairwise multiplication, but then an addition, plus an addition of those products. Okay, so we're going to say we want 3 lots of $1.30 plus 4 lots of 90 cents plus 2 lots of $1.20. And how would you define that with 2 matrices? So here we are, we have the 1 row by 3 columns matrix and the 3 rows by 1 column matrix. And what we say is we need this to dive down there. So the $1.20 would be next to the 2, the 90 would be next to the 4, and the $1.30 would be next to the 3. If that row dived down that column matrix. And then there we have it. We have them paired up, and we can do a pairwise multiplication, what I said up here, and then we add them up. Now that is a fundamental definition of matrix multiplication. We've taken a very simple example and we're going to expand this. Remember, one of my favourite things about matrices is expandability of our arrays of numbers to expand to accommodate more situations. Okay, that's a really great property of matrices. Okay, so let's come down and let's develop this now and see how we can define it and go on with it. So here it is. Here is our definition. If this row was a matrix was multiplied by this column matrix, you think about it diving down. So A would mate with P, B with Q, and C with R. Think about the matrix diving down, that row matrix driving down that column. And now you can see easily that we have a product AP, and we're going to have some additions in our matrix multiplication. It's multiplication pairwise and then addition of those products. Okay, let's do a bit of expanding of this and see if you can get excited with this. First of all, what I want you to do is to just play with some basic ones here, single row and single column matrices, and just observe what's going to happen there. So I'd like you to pause the presentation now and have a go at these 4 problems. Won't take you long. and I'll take you down below here and show you the solutions. Okay, so moving down now, let's have a look at, here they are. Did you get them right? Just 4 of them. Study those there and see what you think. Right? Remember, rows dive down columns. So you get a pairing up or a mating up of entries, which you then multiply and add. So matrix multiplication consists of pairwise multiplying and then addition or a sum of those at the end. Okay, so let's go on now and have a look. We want to, they've called it more complicated matrix multiplication. No. I want to talk about, what is it? The expandability of anything we define in matrix land. Very, very expandable. So what we're going to do now is to go through and say Lisa needs 2 loaves of bread, usual stuff, 3 litres of milk, 1 tub of butter. We've seen this before. Find the total cost Lisa needs to multiply a number of items by to find the total cost, you need to multiply by their respective cost. So here's the cost in the same order. Remember the uniqueness of each entry in matrix land, so you've got to watch the order in which you do things. So you want 2 lots of 265, 2 loaves of bread, 3 litres of milk, and 1 tub of butter. Okay, so that's how we'd usually do it by hand. And this would get very, very long if we had many, many items. Let's see how we can represent it. Well, we could represent it as we did before. Our quantities matrix, 2, 3, 1, would dive down our cost matrix, $2.65, $1.55, and $2.35. And that would give us our totals matrix. Okay, so that would give us an answer at the end, a single answer. Now what about if she was going to store A? That was store A. Let's say she's going to store B, and let's compare them. Okay, now here's the expandability. We can have this one, this was store A. If we put store B next to it, and we multiply the same row matrix, diving down here, we will get that original one from back up here, $12.30, there it was there. And if we then dive it down this column, rows diving down columns, you'll get a mating up of 2 by 25, there it is, that will end up next to that. 3 will dive down there, and 1 will be there. And we multiply them, and then have an addition, and that's our final matrix multiplication entry. So that would be the total cost at store A, total cost at store B. Hey, guess what? You could have hundreds of stores, couldn't you? And compare those costs. They'd be lined up one after the other. Oh yeah. Expandability of matrix work is a very important property. So let's just check whether we can do this. We've got a row matrix. This is 1 row by 3 columns, and we've got 3 rows by 2 columns. So as long as these match up, that's what we're starting to see now. If those middle, the number of columns here and the number of rows here match up, then it's doable. Why? Because rows dive down columns. Rows dive down columns. Now, if you take a row here, which hasn't got the same number of columns as these rows here, it won't mate up. Oh, might be too many entries, and the row will hit the bottom of the pool as it dives down. Small joke. But can you see it? They must mate up. So the number of columns here must mate up with the rows here. So when it dives down, each has a pairing. Okay, let's go on and expand it a bit more. Lisa's friend Sam needs that. So now, how are we going to do that? Well, now there are 2 dudes buying stuff. So if we make Sam another row in Lisa's row matrix, we're going to have that. And what would you say? Well, let's have a look. What are the multiplications we need? Lisa's total cost is as it was before. 1230 in store A and 1120 in store B. Sam's total cost, comparing them, will be these pairwise times again, in that order. So here it's bread, milk and butter from store A, bread, milk and butter from store B. Hey, why don't we get his row to dive down the two columns? Okay, and if we did, well, let's have a look. Lisa will dive down here first, so that's row 1 and column 1 will give us a row 1 and column entry. Hey, remember the uniqueness, we have to track through who's doing what here. This top entry is Lisa's cost in store A, and now if we do Lisa again, row 1 going down column 2, that's Lisa's cost in store B from before, remember. And now when we take Sam down this row, this is row 1 and row 2 and column 1. That is Sam's cost at store A. And now Sam diving down store B is row 2. Remember, Sam is row 2. I told you before, you're going to have to remember how you've constructed these matrices, because every entry is unique. You've got to track it. So this is Sam diving down store 2, and so this is Sam's cost at store 2. So this, because this is row 2, which is Samland, Sam in A, in store A, because column 1 is store A. This is Sam in store B, because column 2 is store B. And this is Lisa in A, in store A, and this is Lisa in B. Hey, you thought this was very simple and a bit useless maybe, but gee, can you see the power of this? In the expandability, if you had many people, many stores, or wanted to combine entries in that way, this is a powerful tool, particularly if you went back and looked at the fourth part of this presentation of matrices, where you learn about how the calculator or technology in general can handle matrices. This expandability can be handled well with technology. This is going to be very, very powerful. So come down now. And let's look at the formal definition of a product. So if we have an M by N matrix and an M by P matrix, then the result is an M by P. Let's have a look at that. Why is that so? An M by N matrix being multiplied by, so this is a matrix, being multiplied by an M by P. Well, you can see the rows in this will dive down the columns in this one. So therefore this is the columns in the first one must made up with the number of rows in this one, so they can dive down. And what are you going to get at the end? Well, you'll have M rows here, M rows from that one, and N and P, columns from this one as a result of all that diving down. And so here's our definition. A bit hard to understand here. The element in the rth row and cth column is the sum of the products in the rth row of A with the corresponding elements in the cth column of B. I would prefer you, now that's true, but I prefer you to think of that in matching up rows dive down columns. That's what it's saying, trying to explain how an element in the rth row and cth column is produced. Okay, so let's have a look now at this happening here with AB. That row dives down the first column. So this is row 1 and column 1 gives you this entry, row 1, column 1, and they would made up, wouldn't they? A and B would end up there, diving down. So it'd be AP plus BR. Let's go and do row 1, column 2, diving down. A would land next to Q and B next to S. So it would be AQ plus BS. So this would be the entry row 1, column 2. So you know where to put it in the new matrix. Okay, let's have a look at row 2, and that will dive down column 1. So you'll produce row 2, column 1 entries, and that'll be CP plus DR. And then when row 2 dives down column 2, you'll produce the row 2, column 2 entry there. So that row diving down column is a good practical way of looking at it, and we must have what's up top here. This must work. You must made up those middle parts of our size statements of this is the size or order of the matrices. The number of columns of the first one must match up with the number of columns, number of rows, of the second one, because the row is going to dive down the column and match up in that way. Okay, come on down now and let's have a look at some examples. So here are some simple ones. Find A times B. Well, first of all, let's check it out. Yes, A is a 1 row by 3 columns, and B is a 3 row by 1 column. So the result should just be a 1 by 1 or a single number. And this is what we did before. This row is going to dive down here. So it's going to be 1 by 2 plus 3 by 4, 5 by 7. And you add them. Remember, matrix multiplication is the addition of some pairwise sums of entries of pairwise sums. It's diving down. Okay, so it isn't just multiplication of numbers here. Okay, and so we get a matrix with 49 as the answer. It's a 1 by 1. Now, A is a 1 by 3 and C is a 3 by 2. Can you remember this? It's got 3 rows and 2 columns. So let's check it out. Yes, they mate up. If we have this row in A diving, it will match up down here perfectly. So it's doable. We say that the matrices conform under the process of multiplication. They conform. They will match up. And so here's the first one. This is row 1 and column 1. Row 1, column 1, or entry A11, sometimes we say there. And over here, when we do it to column 2, we've got 1 row, but now it's diving down column 2. We call that entry 1, 2. So as it goes down there, how does it mate up? Well, let's have a look. The 1 would be there, the 3 would be there, and the 5 would be there. So it's 1 by 1 plus 3 by 2 plus 5 by 1. And then you can see in the second column, 1 by 0, there it is, 3 by 3, yep, and 5 by 4. So we end up with a 1 row 2 column matrix, and that's what we've worked out up here. You can sort of cancel those out and say what you're going to have left is a 1 row by 2 columns, and then that's what we've got. 1 row and column 1 and column 2 there. Time for you to have some practice. Come on down now and let's have a look at some problems here. So here's question 1 to 4. You might have a go and see what you think. It's just examining whether you remember rows dive down columns. I want you to get sick of me saying that so that you're going to remember it in your sleep. Rows dive down columns. So they have to be the right way around to match up. They have to conform. Okay, so pause the presentation, have a go at those 4, and I'll take you through the others now. So as we come down 5 and 6, back to utilising. This is a bit of a utility subject. Let's utilise this basic maths in a practical way, and there's some practical problems here. So pause it, have a go at 5 and 6. Coming down now, we've got question 7. And then I'll go and show you the answers and we'll move on. So you might like to pause the presentation and have a go, and I'm taking you to the answers now. Okay, so the answers are there. That's question 1 to 4. You can pause that and check it out. Coming down, we'll go to 5. Oh, there they are, 5, 6 and 7, I think. Can we get them all on? 4. Oh, there's the beginning of 5. I'll just pause that there and come up just that last bit for 7. All right, so mark your work and see what you think. Might have to go back over the presentation and check it out. I'm going to go on now, so come with me on the next stage of the journey here. And what we've got here goes back to that I think it's the 4th presentation, isn't it, where you're using technology with matrices, or the calculator Casio it was in that entry. So this is something that could be done by hand, but generally when we get up to this size, where in multiplication and addition, we generally will use technology. Just make sure with technology, you must be able to recognise the size of this. So this is a 4 row by 4 column that's being multiplied by a 4 row by 1 column. So they will match up. That's good. Notice you wouldn't be able to do it the other way around. It would not conform the other way around. And the answer should equal a 4 by 1. So a 4 row by 1. So it should look like this, shouldn't it? 4 rows and 1 column when you do it with technology. So you've got to have your wits about you even with technology to get the size of the matrix right. So have a go at question 1. The answers will take you down there in a minute. And then question 2, and pause it as you like, and then question 3 and 4. I think we can fit 3 on, and we'll go to 4. Okay, 4, and come down to 5 now. Can we get it all on? Yep. Well, let's try again. There's 5. Got all of 5 on there. Let's go quickly through and see what you think. They're getting big, but we've got technology on board for this one. Okay, so let's go down and have a look at the answers. Okay, so there's question 1 and 2. Just check those. And we'll just come down a bit. Coming down to question 3. Can we get question 3 and 4 on? I'll get most of it. Question 3. Start of question 4. Let's just check out the rest of question 4. There's the rest of question 4. Coming down now to question 5. Let's see if we get a bit more on there. Question 5A and B. And then part C. All right, so have a go. We're going to go on. We've done our multiplications now. I hope you're getting excited. Can you see the expandability of this? Anyway, let's go to the next level now with this, and that's to do a little bit more investigation of multiplication. And so here's 10C4, and what we're going to do now is we're delving into what I've called the introduction to algebra in matrices land, in matrix land now. Intro to algebra. Like, can we start just talking about matrices in the symbol form where the capital letter in bold means a matrix? And we'll start playing around. Look down here, prove this expression. This sort of thing here. So this is just nothing new conceptually now. It's just playing with various matrices. Here's a 0 matrix here, and there's some interesting ones later on as we come down here. So you might pause it and have a go at those 3. We'll come down now and have a look at question 4, 5, 6 and 7. This is an interesting matrix. You might like to use that up here somewhere. Just thinking about that. We're just looking at the arrangement of entries in a matrix and how that might affect how we multiply and the expressions we can come up with in matrix land. Okay, pause presentation, have a go, and I'll give you the solutions now down below. So here's question 1 and 2 to 3A, but there's a bit more coming up in 3, so you might pause that and check it. So there's 3, what have we got? 3 A, B, end of A, B and C there. And D. And we'll come on to question 4 now. Question 4 and 5. We go to 6 then. Okay, I hope you're going well there. Let's move on and have a look now at comparing ordinary algebra. Well, this is really the algebra with real numbers in the real number set, compared to algebra using matrices. Okay, so the symbols look similar, but just remember the bold letters now, A and B, imply arrays of numbers. We don't know how big they are, but we've got arrays of numbers. Whereas over here, these symbols just mean real numbers times together. We'll just come back down here and have a look at that. So here, can you see by now that AB would not be equal to BA? Well, let's have a look at that. If we had matrix A, let's make them both square. Okay, so if this was matrix A and this was matrix B over here, whatever those entries might be, that row would dive down that column to make your first entry, row 1, column 1 in there. Now that pairing up would be different, wouldn't it, if we put B first and then A. Can you see it? These entries now would be different pairings. This row would go down the first column of A. And so that first entry there, row 1, column 1, for our product AB and BA in this case, would be different. They'd be different pairings as the different row dive down a different column. Okay, because this first entry would be row 1 of A diving down column 1 of B. Done this way, it would be row 1 of B diving down column 1 of A. Different pairings. So therefore, here what we say is matrix multiplication is not commutative. Right, remember the rule A times B equals B times A in real number land implies multiplication is not dependent upon order. And when a process in mathematics is not dependent upon order, we say it is commutative. Commutative. You can commute it, you can change it around, change the order of the terms around. Okay, now in real number land, if you multiply by 0, the number disappears. Any number times 0 is 0. Now here, if you multiply by the 0 matrix, let's have a look at that too. Let's just clean this up a little bit here so you can understand this one. So what we're doing is we've got a matrix, let's call it matrix A. Again, let's just make it square. And the 0 matrix is that. As that row dives down that column, what are you going to get? Well, all these products will be by 0, so that's going to be 0. And then you do it again for each entry. They are all going to be 0 products. And when you add those little pairwise products, you're going to get the 0 matrix. So there is an equivalent to 0 of real numbers in matrix land. We've already seen that the associative rule does hold. You've got to go A by B and A by C. And then in the same way, here A by C and B by C. Okay, so it's important now that the order of multiplication is preserved, right? Because of this one up here. AB is not equal to BA, so you can't play around with C being on the other side. That's something different. Okay, so we've got to be careful about that. We can't put C on the other side because the order in which we multiply matrices is special. It's going to give you a different answer. So here, as long as the order of these pairings is all the same, they will come out the same. You can do A being times by C. That'll be the same as A times BC. What you can't do is change the order there. So let's just unpack that. In real number land, ABC is the same as CAB, but in matrix land, ABC, where A is times by B and then by C, is not equal to C times A times B. It may not even work, because these two may not conform. So the order here, order is important. Watch out for your pairings, the pairings of the matrices you're going to multiply. So here this is okay, this is to the left, and then finally, but now we've stuck C to the, instead of on the right of this product, is on the left. So the ultimate rows diving down columns, pairings, will be different. Okay, so watch for that. Just keep in mind what we're doing. Rows diving down. Are you getting sick of this yet? Diving down columns. Rows diving down columns. Brings a special order to the products. Okay, let's have a look at the identity. That is, a matrix, when you multiply any matrix by in either order, so this is commutative when you're using this one, then you get that matrix back again. Okay, let's just check that out over here now. So here, if we took a matrix A and we go 1 and 0, 0, 1, and these entries dive down there, what will we get? So it's got to be square, because we want it to work either way around. It's got to be a square matrix, so that we can work it the other way around. So here, as we dive down there, it'll be that by 1 and that by 0. So it'll still be this original entry up here, row 1, column 1. Then at row 1 diving down column 2, that will wipe out, and this entry will be preserved. So the entry there will still be the same. That's not 0, that's this entry up here. So can you see that particular combination from that last exercise will preserve, with the zeros in the right spot, those entries. And if we did it the other way around, it will still conform. Of course, these are square matrices now, and these entries, whatever they are, here, that diving down that entry, we should put across in there, that entry would be preserved over here, and plus nothing else, and so on. So we will get the commutativity that we want here, AI being equal to IA. Doesn't matter where you stick this special matrix, then it will preserve the other matrix. A times I will give A. And of course we can, expand it, I got that word again, and expanding it, you would have to have a matrix like this for a 3 by 3 case. That would be your I matrix, the identity. The value, like the value over here, come over here, 1, which no matter which way around you multiply a number by 1, it's a multiplicative identity, they call it. So the multiplicative identity in matrix land is 1, 0, 0, 1, or you can expand it. You might like to think about what would it be for a 4 by 4 to make it work. Can you just think about that? Yeah, what about this? Do you think? And then 0, 1, 0, 0, 0, 0, 1, 0. Do you think? Is this what we need? I think so. And that would be a 4 by 4 identity. Okay, so what about powers of real numbers over there, and powers of matrices? Now, if you have powers of matrices, it means the same thing. You're going to multiply A by itself. Well, this is an integer here. We don't have negatives here. Well, we do have negative powers. It means something different, though. We'll have a look at that later on. But A to the n would mean these all line up n times. Now just notice it must be square, because otherwise you can't actually multiply a matrix by itself. Let's have a look at that. Let's just come over here and just make sure of that one. Let's say matrix A is a 3 by 2. Okay, so that's 3 rows, 2 columns. If we try to multiply it by itself, so we'll call this same 3 rows, no, it's the same 3 rows, so let's just use a cross. 3 rows and 2 columns. Okay, so here when we try to dive down there, it doesn't get to the bottom. It does not conform. A 3 by 2 cannot be multiplied by itself because it won't conform, won't mate up in there. The rows won't match the number of columns here, won't match the rows there. So when a row dives down the column, it's going to miss out. Okay, so to repeatedly multiply by a matrix, that matrix must be square. Are you getting the hang of this? Hasn't it exploded absolutely into a huge area of mathematics now? Let's go on and have a look at some examples, and we'll finish up soon with you doing some. So expand and simplify where possible here. Well, a plus 2i all squared, there it is, multiplied by itself as usual, and we can do this. So it's that by that. We split it, yes, so there. And then that bracket by the 2i, and then a by a is a squared, 2i by a, 2ia, and now a by 2i. That technically should be a, 2i, but you can put the 2 in front. We know the scalar multiplication rule. And then 2i by 2i is 4i squared. And then down here, 2ia, I by a is I by a, is a, I leaves a unchanged, so it's 2a, and 2ai, a by I is a. I is, remember, the multiplicative identity, it doesn't change it, and I squared, I times I is by definition, right, remember, this matrix which doesn't, when anything's multiplied by it, it doesn't change it. So if I is multiplied by itself, it must give just I. So it's 4i, and there's our simplification. So all of a sudden now, we're doing sort of equations and expansions, algebra type operations in matrix land. Interesting stuff. Let's look at A take B all squared. It's A take B by A take B. They're making the idea here that the definition of a square in matrix land is the same thing. It's repeated multiplication by the same matrix. So let's split it now. We've got A take B will be multiplied by A, and then A take B will be multiplied by B, and we've got this take sign in the middle. So we can do that. We could do it another way. You could say that's A by A take B by A take B. That will also give you the same answer, thinking about that associative rule and expansions. What we can't do here, when we've done this, let's do it. A by A is A squared, neg B by A is neg BA, neg here now neg and B by A by B, sorry, you've got to keep it in the pairwise association, the same sides. This would be neg AB because A is on the left, and then B by B, oops, hang on, let's just check back up here now, we've slipped a bit. I come here, so here we've got B squared, we'll just get rid of that. Okay, so we've got B squared there, and let's have a look then at our final answer. We can't go any further than that because AB is not equal to BA down there. All right, let's have a look at doing some like that. So here are some expressions, probably worthwhile doing, I guess, a fair bit of those. Not real happy with doing all of them perhaps, but you could have a go at all of those and see what you think. And then we'll come down and have a look at this example here with example 8. Okay, let's have a look at the example 8 here now. We've got these conditions, a squared equals 2a plus 3i, and we want to find a cubed and a to the fourth in this form. So let's have a look now, writing it out. Now, we want a cubed, so a cubed is a by a squared. So that's a by, or we'll pop the a squared in there. So the secret in this work is looking at the pairings, right, pairings, and then you need to sub in given information at the right time. So here we said we wanted a by a squared, and we notice a. That's what we were given. So pop it in there, and now this will be a by 2a or 2a squared, a by 3i, 3ai, and that a should be to the left of I because it's to the left of I up here. Watch the pairings and the order. Orders are important here. But it doesn't matter with I because AI or IA are still just going to give you A there. So let's have a look here. So what have we got? Well, we've got with our A squared, then putting 2a plus 3i back in again, and then 3ai is just 3a. So there's some tricky do's here of knowing when to come over here, how to pair, and watch the subbing in of the given information, because we put it back in here to get our required result. Okay, breaking it all down into Ka and Li. So here's our indication here that we want to have A's and I's only in there. So let's look at a to the fourth. So we're going to say a to the fourth is a by a cubed, and we've just found a cubed. Okay, otherwise we have to go right back and do it like this, a squared by a squared, and it will still work out, right? So we would do it like that, if you wish, because a to the fourth is a by a cubed, if you want to relate it back to this one. If you were doing it just starting out by itself, it'd be a squared by a squared, because you're given a squared. All right, so you could do that. So here, it's a by 7a is 7a squared, and then a by 6i is 6ai, keeping the order of the multiplication of the matrix correct. So if a is to the left, it's got to stay to the left there. And then we can replace a squared again by 2a plus 3i. So it's just playing around. Algebraic trickery here, I think. Do you want to have a go and see how tricky you can be? Let's have a look down here at question 9. Well, we've got a few questions here. So 9 and 10, come scroll down a minute to 11. So probably you want to try most of these to get the hang of matrix algebra. Okay, 11 and 12. Have a go at those and see what you think. It's looking back at algebra in terms of expansions in real number land and solving equations. We're going to be doing that now. Hasn't matrices really grown just in the short time you've known it? Here we go. So let's have a look at example 9. Find constants a and b such that a squared equals a times a plus b times I, and a is that. So let's work out what a squared is, times it by itself. And if we do that, coming down the left-hand side, we get that. And we want to put it equal to a lots of a and b lots of I. So you just set up that structure. And scalar multiplication, a by 1, a by 2, get 2a, so all multiplied by a there, and the b's pop up there, b times naught is naught, so those are still zeros there. So you're just doing a combination of the basic operations, multiplying by a scalar. These are scalars, A and B. Because they're non-matrices, they don't have the order and nature of a matrix, so therefore they are called, an ordinary number is called a scalar. similar to in vector land. So now let's do the addition. We find that these are the 4 entries. Now we must check out every one of the 4 matings up, because a matrix is equal to another one only if each individual and unique entry, row 1, column 1, must equal row 1, column 1 in the other matrix, and so on. All of them must mate up. So A plus B would be 7, 2A equals 10, so that's okay. Therefore A is 5 from that one, and B is 2. Solving those two, 2A is 10, so that'll give you A is 5, and then stick 5 in here. B would be 2. And now you've got to check the bottom row. So the bottom row, 3A, 3 times 5 is 15, which checks. 4A plus B, this entry here, should equal 22. So you've got to put those checks in. Don't just grab the first 2 equations, get a potential A and a potential B and forget it. It may not work in the other spots. You have to show it. So check all entries to make sure the matrices are perfectly equal, if you like. Okay, come down, use that tool now, and have a go at 13 and 14. And of course, now I'll take you down to the solutions. Through the solutions now. So here they are, starting at question 8 for this little batch. 9. Okay, 10 then. Okay, 11. And we'll just bring it down a little bit more perhaps. See if we can get it there. Yep, 11. And 12, a bit of 13. Let's see if we can get 13 up there. Yep, 13. And 14. There's 14. All right, so it certainly is an expanding area, isn't it? You know, I like that word expanding for matrices. Anyway, so I hope you have enjoyed this and are enjoying building up your skills. It's getting good. So for now, it's cheers from me. I'll catch you in the next presentation, which is further algebra in matrix land. Cheers.